rather than a fish or a mouse. You know, I'm making this a little bit of a simple story because there are still neurons in primary visual cortex. We don't know what they like. They don't like simple oriented bars. But by and large, the Hubel and Wiesel found that the beginning of visual processing is not a holistic fish or mouse. The beginning of visual processing is simple structures of the world, edges, oriented edges. And this has a very deep implication to both neurophysiology, neuroscience, as well as engineering modeling. It's if later when we visualize our deep neural network features, we'll see that simple edge-like structure emerging from our model. And even though the discovery was in the later 50s, early 60s, they won a Nobel Medical Prize for this work in 1981. So that was another very important piece of work related to vision and visual processing. And so when did computer vision begin? That's another interesting story, history. The precursor of computer vision as a modern field was this particular dissertation by Larry Roberts in 1963. It's called Block World. He, just as Hubel and Wiesel were discovering that the visual world in our brain is organized by simple edge-like structures, Larry Roberts, as an early computer science PhD student, were trying to extract these edge-like structures in images, and as a piece of engineering work. And in this particular case, his goal is that, you know, both you and I as humans can recognize blocks no matter how it's turned, right? Like, we know it's the same block. These two are the same block, even though the lighting changed and the orientation changed. And his conjecture is that, just like Hubel and Wiesel told us, it's the edges that define this this structure. The edges define the shape, and they don't change, rather than all these interior things. So Larry Roberts wrote a PhD dissertation to just extract these edges. It's you know, if you work as a PhD student in computer vision, this is like, you know, this is like undergraduate computer vision. Wouldn't have been a PhD thesis, but that was the first precursor computer vision PhD thesis. Larry Roberts is interesting. He kind of gave up his work in computer vision afterwards, and went to DARPA and was one of the inventors of the internet. So, you know, he didn't do too badly by giving up computer vision. But we always like to say that the birthday of computer vision as a modern field is in the summer of 1966. In the summer of 1966, MIT Artificial Intelligence Lab was established. Before that, actually, for one piece of history, you should feel proud as a Stanford student. There are two pioneering artificial intelligence lab established in the world in the early 1960s. One by Marvin Minsky at MIT, one by John McCarthy at Stanford. At Stanford, the artificial intelligence lab was established before the computer science department. And Professor John McCarthy, who founded AI Lab, is the one who is responsible for the term artificial intelligence. So that's a little bit of a proud Stanford history. But anyway, we have to give MIT this credit for starting the field of computer vision, because in the summer of 1966, a professor at MIT AI Lab decided it's time to solve vision. You know, so AI was established. We start to understand, you know, first order logic and all this. And I think Lisp was probably invented at that time. But anyway, vision is so easy. You open your eyes, you see the world. How hard can this be? Let's solve it in one summer. So, especially MIT students are smart, right? So the Summer Vision project is an attempt to use our summer workers effectively in the construction of a significant part of a visual system. This was the proposal for that summer. And maybe they didn't use their summer worker effectively, but in any case, computer vision was not solved in that summer. Since then, it became the fastest growing field of computer vision and AI. If you go to today's premium computer vision conferences called CVPR or ICCV, we have like 2,000 to 2,500 researchers worldwide attending this conference. And a very practical note for students, if you are a good computer vision / machine learning student, you will not worry about jobs in Silicon Valley or anywhere else. So it's actually one of the most exciting fields. But that was the birthday of computer vision, which means this year is the 50th anniversary of computer vision. That's a very exciting year in computer vision. And we have come a long way. Okay, so continue on the history of computer vision. This is a person to remember, David Marr. He was also at MIT at that time, working with a number of very influential computer vision scientists, Shimon Ullman, Tommy Poggio, and David Marr himself died early in 70s. And he wrote a very influential book called Vision. It's a very thin book. And David Marr's thinking about vision, he took a lot of insights from neuroscience. We already said that Hubo and Wiesel give us the concept of simple structure. Vision starts with simple structure. It didn't start with a holistic fish or holistic mouse. David Marr gave us the next important insight. And these two insights together is the beginning of deep learning architecture, is that vision is hierarchical. You know, so Hubo and Wiesel said, okay, we start simple. But Hubo and Wiesel didn't say we end simple. This visual world is extremely complex. In fact, I take a picture, a regular picture today with my iPhone. I don't know my iPhone's resolution. Let's suppose it's like 10 megapixels. The potential combination of pixels to form a picture in that is bigger than the total number of atoms in the universe. That's how complex vision can be. It's really, really complex. So Hubo and Wiesel told us start simple. David Marr told us build a hierarchical model. Of course, David Marr didn't tell us to build it in a convolutional neural network, which we will cover for the rest of the quarter. But his idea is this: to represent or to think about an image, we think about it in several layers. The first one, he thinks we should think about the edge image, which is clearly an inspiration, took the inspiration from Hubo and Wiesel. And he personally called this the primal sketch. It's, you know, the name is self-explanatory. And then you think about 2.5D. This is where you start to reconcile your 2D image with the 3D world. You recognize there is layers, right? You know, I look at you right now. I don't think half of you only has a head and a neck. Even though that's all I see, but I know you're occluded by the row in front of you. And this is the fundamental challenge of vision. We have an ill-posed problem to solve. Nature had an ill-posed problem to solve because the world is 3D, but the imagery on our retina is 2D. Nature solved it by first a hardware trick, which is 2 eyes. It didn't use 1 eye. But then there's going to be a whole bunch of software trick to merge the information of the 2 eyes and all this. So the same thing with computer vision. We have to solve that 2.5D problem. And then eventually we have to put everything together so that we actually have a good 3D model of the world. Why do we have to have a 3D model of the world? Because we have to survive, navigate, manipulate the world. When I shake your hand, I really need to know how to, you know, extend out my hand and grab your hand in the right way. That is a 3D modeling of the world. Otherwise, I won't be able to grab your hand in the right way. When I pick up a mug, the same thing. So that's David Marr's architecture for vision. It's a very high-level abstract architecture. It doesn't really inform us exactly what kind of mathematical modeling we should use. It doesn't inform us of the learning procedure, and it really doesn't inform us of the inference procedure, which we will get into through the deep learning network architecture. But that's the high-level view, and it's an important concept to learn in vision, and we call this the representation. A couple of really important work, and this is a little bit Stanford-centric to just show you. As soon as David Marr laid out this important way of thinking about vision, the first wave of visual recognition algorithms went after that 3D model, because that's the goal, right? Like, no matter how you represent the stages, the goal here is to reconstruct that 3D model so that we can recognize object. And this is really sensible, because that's what we go to the world and do. So both of these two influential work comes from Palo Alto. One is from Stanford, one is from SRI. So Tom Binford was a professor at Stanford AI Lab, and he and his student Rodney Brooks proposed one of the first so-called generalized cylinder model. I'm not going to get into the details, but the idea is that the world is composed of simple shapes like cylinders, blocks, and then any real-world object is just a combination of these simple shapes given a particular viewing angle. And that was a very influential visual recognition model in the 70s. And Rodney Brooks went on to become the director of MIT's AI lab, and he was also a founding member of the iRobot company and Roomba and all this. So he continued very influential AI work. Another interesting model coming from local Stanford Research Institute, I think, SRI, is across the street from El Camino, is this pictorial structure model. It's very similar. It focused, it has less of a 3D flavor, but more of a probabilistic flavor, is that the objects are made of still simple parts, like a person's head is made of eyes and nose and mouth, and the parts were connected by springs, allowing for some deformation. So this is getting a sense of, okay, we recognize the world. Not every one of you have exactly the same eyes, and the distance between the eyes, we allow for some kind of variability. So this concept of variability start to get introduced in a model like this. And using models like this, you know, the reason I want to show you this is to see how simple the work was in the 80s. This was one of the most influential model in the 80s, recognizing real-world object, and the entire paper of real-world object is these shaving razors, and but using the edges and simple shapes formed by the edges to recognize this by David Low, another Stanford graduate. So that's kind of the ancient world of computer vision, when we have been seeing black and white or even synthetic images. Starting in the 90s, we finally start to move into like colorful images of real world. What a big change. Again, a very, very influential work. here is not particularly about recognizing an object, it's about how do we like carve out an image into sensible parts, right? So if you enter this room, there's no way your visual system is telling you, oh my God, I see so many pixels, right? You immediately have grouped things. You see heads, 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 chair, 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 a stage, platform, piece of furniture, and all this. This is called perceptual grouping. Perceptual grouping is one of the most important problems in vision, biological or artificial. If we don't know how to solve the perceptual grouping problem, we're going to have a really hard time to deeply understand the visual world. And you will learn towards the end of this class, this course, a problem as fundamental as this is still not solved in computer vision. Even though we have made a lot of progress before deep learning and after deep learning, we're still grasping the final solution of a problem like this. So this is again why I want to give you this introduction for you to be aware of the deep problems in vision, and also the current state and the challenges in vision. We did not solve all the problem in vision, despite whatever the news says. You know, like we're far from developing terminators who can do everything yet. So this piece of work is called Normalized Cut. is one of the first computer vision work that takes real world images and tries to solve a very fundamental difficult problem. Jitendra Malik is the senior computer vision researcher, now professor at Berkeley, also Stanford graduate. And you can see the results are not that great. Are we going to cover any segmentation in this class? Probably. We might, right? You'll see we are making progress, but this is the beginning of that. Another very influential work that I want to bring out and pay tribute. For, even though these work we're not covering them in the rest of the course, but I think as a vision student, it's really important for you to be aware of this, because not only it introduces the important problem we want to solve, it also gives you a perspective on the development of the field. This work is called Viola-Jones face detector, and it's very dear to my heart because as a graduate student, fresh graduate student at Caltech, it's one of the first papers I read as a graduate student when I entered the lab and I didn't know anything, and my advisor said, read this amazing piece of work that we're all trying to understand. And then by the time I graduated from Caltech, this very work is transferred to the first smart digital camera by Fujifilm in 2006 as the first digital camera that has a face detector. So from a technology transfer point of view, it was extremely fast, and it was one of the first successful high-level visual recognition algorithm that's being used by consumer product. So this work just learns to detect faces, and faces in the wild. It's no longer simulation data or very contrived data. These are any pictures, and again, even though it didn't use a deep learning network, it has a lot of the deep learning flavor. The features were learned. The algorithm learns to find features, simple features like these black and white filter features that can give us the best localization of faces. So this is a very influential piece of work. It's also one of the first computer vision work that is deployed on a computer and can run real time. Before that, computer vision algorithms were very slow. The paper actually is called real-time face detection. It was granted Pentium 2 chips. I don't know if anybody remember that kind of chip, but it was on a slow chip, but nevertheless it ran real time. So that was another very important piece of work. And also one more thing to point out, around this time, this is not the only work, but this is a really good representation. Around this time, the focus of computer vision is shifting. Remember that David Marr and the early Stanford work was trying to model the 3D shape of the object. Now we're shifting to recognizing what the object is. We lost a little bit about, can we really reconstruct these faces or not? There's a whole branch of computer vision graphics that continue to work on that. But a big part of computer vision is not, at this time, around the turn of the century, is focusing on recognition. That's bringing computer vision back to AI. And today, the most important part of the computer vision work is focused on these cognitive questions like recognition and AI questions. Another very important piece of work is starting to focus on features. So around the time of face recognition, people start to realize